Hey everyone, welcome back to my new video. I am Ddco, studying in Shri Venkateshwar College of Engineering, and my lesson is 43, and my semester is third sem, and my course code is BCS302, and my course title is Ddco, and my topic is about KMAP. Let us discuss about some uh, about the KMAP method. The KMAP means it's called officially called as Karnayoga map. It is visual and diagrammatic tool used to simplify Boolean equations. The method converts the truth table of Boolean function into graphical, making it easier to identify simplifications. Purpose: the K-map method helps reduce complex Boolean expressions into their simpler forms using visual groupings. It's an alternative to algebraic simplification. How it works. Square represent minterms. A K-map of consists of several squares with each square representing a single minterm. A term of that sum of product form of Boolean expression. Sum of minterms. Any Boolean function can be expressed as sum of minterms. The map helps identify these minterms graphically. Visual grouping. By recognizing patterns in the arrangement of minterms in the K-map, derive the simplest algebraic expression for the function. Minimizing the Boolean equations. The map allows one to visual group adjacent squares to minimize the function, which in turn leads to simplified Boolean expression. The simplified uh, expressions are usually written in one of two standard forms. Sum of product means a form where product and terms are added together. Product of sum. A form where several sum or terms are multiplied. Simplified expression. Sum of products of a. So this form takes and terms and combines the using or operation. Example: AB plus AC AB plus AC AB plus AC. In a circuit, each product corresponds to an AND gate and the overall sum is represented by an OR gate. And now product of sums. In this form, the terms are read first and resulting expressions are combined using AND. Now example is A plus B into A plus C into A plus B into A plus C into A plus B into A plus C. This forms pure OR gates and represents the different logic algebraic expression. The goal of K-map is to reduce to minimum as it reduces the number of literals, variables and terms. Next, another slide. Now it's about the four variable K-map. Structure: a K-map of four binary variables. Example: wx, yz, w. xy, zw, xyz contains 16 square with each square representing one possible combination of these variables. 2 power 4 equal to 16. Now, the rows and columns are labeled in gray code, where only one bit changes between adjacent squares. This arrangement makes it easier to group adjacent squares that differ by just one variable. Grouping squares. Adjacent squares in the KMF can be grouped to simplify the Boolean expressions. One square represents one minterm. Two adjacent squares combine to form a term with three literals. Four adjacent squares form a term with two literals. Eight adjacent squares reduce a term with only one letter. As you show the given figure, solve out the four variable KMF. Okay, now simplification. Process with KMFs. Marking minterms, identifying the minterms from truth table or a function, and place them in the corresponding squares of the K. Now, group adjacent minterms. One group 1, 2, 4, or 8 adjacent squares that contain minterms. Grouping reduces the number of variables in the expression. Write the simplified expression. Number one, for each group, write down the simplified product and term by considering only variables that remain unchanged across the group. For instance, in a four variable KMF, if two adjacent squares contain m2, m2, m2 and m3, 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 the variables corresponding to the squares that simplify of 4 literals, 2 literals, 3 literals. Now, problem statement. We need to simplify this Boolean function. Like f of wx y z is equal to the summation of 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. This means the function is exposed as sum of minterms for the given term. As it shows, it is in table of k map, and as you see the figure 3.9 map example of is the expression is simplified expression y or wz is equal to x. Now it's a step creating a form. Step one, create four variable kmap. Since the function has four variables w, x, y, z, the kmap will contain 16 cells. Since 24 equal to 162 into 4 is equal to 1624 equal to 6. Each of the numbers listed corresponding to a minter that needs to be placed in the kmap. The map is usually set up in a way that adjacent squares differ by only one variable using gray code. Mark ones in the corresponding position of kmap. For minterms 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, and 14. Now, step 2, grouping the ones. The goal is combined adjacent square to minimize the Boolean equation. Each adjacent squares with ones are combined to form a single group. This group simplifies in a term that only one literal y dash y dash y dash. Why? Because the right 8 adjacent squares cover all possible values of w, x, y, z, leaving only y, 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 and unchanged. There are three remaining on the other side of the game. This cannot be grouped in one larger group, but can be grouped to groups for four adjacent squares. Now, step 3, minimization of remaining groups. The twos, ones right on the group it is twos, ones on the top left to the form w dash y dash z dash w dash z w dash z dash. This group combines two columns, eliminating the variables x x x and y y y and w dash w w dash and z dash z. Another group is formed by combining four squares for the middle rows and the two end columns, resulting in the term of x z dash x z dash. Final simplified Boolean expression. The complete simplified Boolean expression is f of w x y z equal to y dash plus w z plus x z dash f of w x y z y z of w dash z and x z of f of w x y z equal to y dash plus w dash z dash plus x z dash. Summary of simplification. Number one, identifying the minterms and plot them on the schema, and grouping the largest possible subgroups of 2 like 1, 2, 4, 8. Write down the simplified terms by observing which variables take on across the group. The larger of the group for literals appear in the term. This method reduces complex Boolean expressions into simplified terms, making it easier to design circuits with fewer gates. As you saw in the figure 3.10, this is a perfect example. So, last conclusion is about the K-map is a graphical tool that helps minimize expressions by visualizing, grouping, adjacent simplified expressions either in SOP or POS form, both reducing the complexity of a digital circuits. A variable K-map has 16 squares with each square representing combination of four binary inputs, and adjacent squares can be grouped to minimize the Boolean function further.